Section 2.7, Applications of Derivatives to Business and Economics. Now the approach that we're about to take is oversimplified, and so recognize that this is more of the idea, but there's a lot of stuff happening in the background, and so we're probably ignoring a lot of important factors. But in our oversimplification, we're just going to assume that C is the cost of producing X units of a product, R of X is the function that's the revenue generated by selling X units of a product, and then if you want to find the profit, that's the revenue minus the cost. Well, the idea is remember that we talked about marginal functions, and so specifically we're going to say that the marginal cost is the derivative. And so specifically when we say marginal, what we mean to say is that we're really trying to think about the approximate amount of change that would occur at one unit near the location that we're talking about. Like I said, oversimplified. Well, then what's going to happen is the idea is that you want to minimize cost, maximize revenue. That's really the whole theory behind running a business. And so to find the minimum marginal cost, you're going to take the derivative again to get the second derivative, C double prime of X, and set it equal to 0. And so recognize that if we're working with the marginal cost function, that's C prime, you're really going to be able to find information about the cost function itself. Then in our simplification, revenue functions are going to deal with the money that comes in. And so similar to the cost, to find the marginal revenue, take the derivative of the revenue function to get R prime of X. And then if X units of products are sold at a price P per unit, then the total revenue R of X is given as X times P. Where specifically the demand equation, where P is some function, determines the total revenue function, specifically R of X is equal to X times P, which is really equal to X times whatever this demand function is. So then let's play with an example. Hot dogs at the baseball field usually sell for $3.60 each. The hot dog stand sold an average of 12,000 on game night. However, when the price was raised to $3.90, hot dog sales dropped off to an average of 10,500 per night. Assuming a linear demand curve, find the price of a hot dog that will maximize the nightly hot dog revenue. Okay, so what are we going to deal with? Well, let's think about the demand equation. And so let's state that P, which is our demand equation, is really going to be related to the price of a hot dog. And then recognizing that X is really the number of hot dogs sold. Now, the fact is that they told us we're going to assume that there's linear demand. And so linear, meaning specifically that my P, or my f of x, whichever way you want to think about it, is linear, and that is specifically we're going to have some form P is equal to m times x plus b in the end. Now we may have to do a little bit of work to find that using point slope form, but recognize that we will get a P function that is a line. Alright, so since that's our goal, just to conserve space, I'm going to erase that for now. Let's think about our slope. Well, what's our slope going to be? Well, specifically, if our input x is the number of hot dogs sold and the output is the price of the hot dog, then linear means we want to know what is the slope. So the slope, y sub 2 minus y sub 1 over x sub 2 minus x sub 1, where y is the price and x is the number of hot dogs, let's just use the information given. So specifically, note that they changed the price to $3.90, and on the night that they sold the hot dogs at $3.90, then there were only 10,500 sold. Well, then, notice that the other point we're going to use is that when they sold the hot dogs at $3.60, they sold 12,000 hot dogs. And so specifically, we then get 3.9 minus 3.6, which is 0.3 divided by negative 1,500. And then if we're looking for a slope, I can find this. This is 0.3 divided by negative 1500, or specifically negative 0.00002. Now at this point, my claim is that P is then equal to this slope that we just found, negative 0.0002 times x plus some y-intercept b. Well, we could use the point slope form, or we could just use one of our ordered pairs that we were already given. That is, if the price point was 3.6 when 12,000 were sold, so that's negative 0.0002 times 12,000 plus that y-intercept b, we can then solve for b. So this gives me that 3.60 is equal to negative 2.4 plus b. Add 2.4 to both sides. Add 2.4 to both sides. And so we get that 6 is equal to b. So that my demand equation, P, is now equal to negative 0.0002 x plus 6. So that's our demand equation. Well, then recall we're trying to maximize the nightly revenue. Our revenue function is going to be x times p, where p is our demand equation. And then that's going to give us x times negative 0.0002 x plus 6, which is then equal to negative 0.0002 x squared plus 6x. Since we're trying to maximize that revenue, what do we need to do? We need to find the marginal revenue function, r prime of x. So that's specifically going to be negative 0.0002 times 2, or 4, x to the first, plus 6. Then I just need to figure out where do my extrema occur. So set it equal to 0. 0 is equal to negative 0.0004x plus 6. Minus 6 from both sides, so I get negative 6 is equal to negative 0.0004x divide by negative 0.0004 divide by negative 0.0004. So then I get that x is equal to 15,000. Now remember that x is representative of our possible extrema, and so if I want to know if it actually is our extrema, that is at a relative minimum, then I can actually find the second derivative to confirm this. So take r double prime of x. R double prime of x is then going to be negative 0.0004, which is negative, and so when we plug in 15,000 here, we know that we have a concave down function, which means that we do have a maximum. That's good. We've confirmed it's a maximum. But since we're really trying to find the price of the hot dog that maximizes the revenue, now that I've found this 15,000 hot dogs would be sold to maximize revenue, then I'm just going to take and plug that 15,000 hot dogs into my price function, which is negative 0.0002 times 15,000 plus 6, and I get that the price of hot dog that should maximize revenue should be $3. And so $3 being that assumption based on linear cost, there we are. Now let's suppose that the hot dog stand has a fixed cost of $2,000 per night, and it has a variable cost of 50 cents per hot dog. Let's find the price of a hot dog that will maximize the nightly profit. So similar approach, but now we're working with profit. And so specifically, what is our cost function now? Well, the cost function, C of x here, is really going to be the 2,000 fixed price plus the 50 cents per hot dog. And so real quick to call attention to this before I write down profit. Earlier I used P, and I really should have used a lowercase p, where P was the price of the hot dog. And so all of these P's that we were talking about here was the price function, not the profit function. So now when I write P down here for profit, maybe I'll just write profit for the moment, I mean that profit is my P function. So if nothing else, just be careful when you write these P's. Make sure you get the big versus the little to get things right. And so if my profit function P of x is really equal to revenue minus cost. Since we know the revenue function already, we found it based on linear assumptions. That's then going to be negative 0.0002 x squared plus 6x. That was our revenue function from earlier. Revenue function. And so now we're subtracting our cost function that we have right here. That's going to be minus 2,000 plus 0.50x. At this point, let's do the arithmetic. This is negative 0.0002x squared plus 5.5x minus 2,000. And so this is going to be our profit function. But then if we're trying to figure out the price of a hot dog that will maximize the nightly profit, I'm trying to find possible extrema, so I need to find the derivative of the profit function. But the derivative of the profit function is going to be negative 0.0002 times 2, or 4, x to the first, plus 5.5. The derivative of a constant is 0. And so then, if this is our profit function, set it equal to 0. 0 is equal to negative 0.0004x plus 5.5. Solve for x, minus 5.5, minus 5.5. So negative 5.5 is equal to negative 0.0004 times x. Divide by negative 0.0004. Divide by negative 0.0004, which I get to be 13,750 is x. Take this x value, plug it back into my price of the hot dog function, p being equal to price of hot dog. Once again, be careful with my p's here, because I've got a profit function p and I've got a price of hot dog function p. And so this is the price of hot dog function p, which is p of 13,750, is this one, which is equal to negative 0.0002 times 13,750 plus 6, which is $3.25. This is what we should charge per hot dog if we're trying to maximize the nightly profit, whereas this is the price that we should charge if we want to maximize the nightly revenue. And so recognize that these things are different, but we just approach them slightly different to find the answers.